You were not recording? Now I said, okay,
now we turn the camera on.
You forgot to push
So I wanted to chat with you for a few minutes because I got a phone call the other day from a customer who is using a cell culture process to make a rheumatoid arthritis medication, right? And
interesting.
You know, the circumstances of the process have changed quite a bit for her.
In what sense?
Well, she's got the upstream people, you know, they're being more and more productive by, you know, changing the nutrient package and, you know, changing the media over and over again, so that now there's a lot more cells in this certain amount of volume that she's got to work with. And, you know, it's gone up a factor of 10. And so this process that has used filtration for so many years is now becoming, you know, really problematic because the filters just can't handle these high cell densities, you know, and each cell
and I assume that she is in the downstream or after upstream stage. Okay.
Yeah, she's in the downstream stage, and you know, the microbiologists upstream, they're clever people. They keep doing more and more, you know, in a certain size volume, and it's become a bottleneck, you know, for her. So she's got to figure out, you know, a better way to do this recovery. Because it's costing them a lot of money. They're using a lot of filtration. It's just not working very well. So the bottom line here is now she's got to deal with maybe 10 times the cell density that she had just a few years ago.
Wow. Seems a trend.
Oh, I agree. And I know you've seen this before as well.
I did. And now so they are producing more and more cells in the upstream. So the cell concentration is going high, right? Am I understanding you correct? And then, why is that? Why they are going for the upstreams to produce more and more cells?
Well, I mean, you know, each cell can only produce, you know, so much of a given protein. So if you want to do more with a given volume of your system or a given capacity of your system, the answer is make more cells.
Yeah.
Sounds easy.
That makes sense.
Yeah. Sounds easy, sounds clean, but it causes
easy
problems.
For whom?
Yeah.
Easy for whom?
Well, it's easy for the microbiologists who have designed all these processes and are making them more and more productive.
Yeah.
The trouble is that now you have all of these cells to generate all of this protein, and after the cells have done the work, now the filtration can't cope.
Yeah. So what was the discussions with her?
Well, yeah, I mean, we were talking about, you know, what the alternatives were if she was going to stay with the filtration type of a system or, you know, perhaps change to a different mechanism in order to get the job done. Maybe look at gravity settling or a sedimentation device that operates with a different mechanism, right? A filter, of course, has the physical barrier, physical membrane between the two phases that you want to make a separation on. And that can work, but filters, again, have only so much capacity for a given volume or given surface area that they have to work with.
They are definitely limited in that sense.
Yeah. So, you know, the answer is you can keep adding more and more filters because the filters have a fixed capacity.
I'm guessing that you were kind of going to the angle of bringing the new alternatives to her, right?
Yeah. I mean that's what we do. So it was, you know, kind of news to her that you know, these perceptions of what a centrifuge technology might be 5 or 10 years ago, it's not the same as is available today.
The whole concept, of course, is using the G-forces and multiply of those with high G-forces to separate, and that was the technology. And when we're talking about the G-forces here, these are actually quite a double-edged sword, especially for biopharma. These cells are really fragile, right? You know better than me. And when we are dealing with a really high G-force, there will be a risk of rupturing these cells.
That's right.
Yeah, and we don't want ruptured cell, right?
No, that just makes the whole problem more complicated than it needs to be.
That's the different small details on the technologies that make a big difference. For example, the hermetic technology, that is a fully hermetic, no air entrapped, and that will reduce the shear forces, and that make it much gentle treatment. So we don't need to be necessarily quite high in a G-force to be effective. we can have the optimum G-force, but use the other advantages, add the other technologies like the hermetic. Literally, we don't need to work harder if we work smarter.
No, I fully agree. And, taking things into and out of the rotating system gently is one thing, but that doesn't really help with these high cell concentrations.
True. And that was one of the main challenges for her, right?
Yep. Absolutely. 10 times the solids load of what you're used to, that's nothing, that's no small problem to deal with.
No.
So we talked a little bit about the idea that, okay, what if we were able not to, have to worry about a capacity of one phase versus the other phase, but what if we were able to take one stream in and two streams out on a continuous basis?
Oh, that's great. So you kind of shift the kind of way of thinking of the solid-liquid separations to actually liquid-liquid. And that's our bactifuge or topstream technology, right? So you're thinking on that path.
No, exactly. So how can we take and shift something from a liquid-solid system to a liquid-liquid system? And that, that's about understanding, the nature of the problem and looking at it in a different way.
Yeah.
And this is something that usually takes us some time to convince people that you can look at it from a completely different perspective and still get the job done in an effective way. But the concept of when you get it up and running and you have the single stream in and the centrate is headed into one direction and the concentrated cell suspension is headed in another direction, it's fantastic. It means we don't have a limitation.
And it's a continuous removal as well, right?
Yeah.
So there's many. I've heard that from many of our customers. That what do you mean is the continuous removal? So at the same time that we can feed in without any interruption and other things, that we can remove the cells out, and said, those can go continuously be recovered without any interruption in the process.
Right, which of course means that once we set up these conditions, it will run continuously. It's not any sort of a batch process or a need to change the operating state and backflush the materials and so forth. You kind of set it and forget it.
Yeah.
And it operates through the end of the run under very controlled and very predictable circumstances. And that, of course, it translates directly into efficiency in terms of recovering the most of the available material.
Yeah, fascinating.
So when we're running with these two continuous streams, right, one in, two out, you get to the end of the process, and now you've got to get into the cleaning steps. And in order to reuse the equipment here for the next time. And, that's where some of the newer ideas that we have on the design of the discs can really help. And, looking at this design, it's obvious that it's a lot more cleanable than some of the old manufacturing methods. And, it provides a really efficient way to ensure good flow over the separation surfaces, that we get the maximum utilization out of the available space.
Exactly. And no welding, much easier to clean, less consumption of the water and chemicals. I think in some of the tests that we have some data also on it, it was up to 15% lower water consumption.
And that's important, right? Nobody ever has enough water these days.
No, exactly. So what did you end up with the conversation?
Well, we got cut off. She had to go. So we need to continue the conversation. And I kept coming back to the same thought. This industry has the problem with the high cell densities, and we've got to show people what's available today and how taking a different approach can have a really big impact on the productivity of the entire process.
Totally agree.